The big news is that around a very nearby, cold, small star, we found 7 rocky, Earth-sized planets, all of which could potentially have liquid water.
Imagine stumbling upon a cosmic treasure chest just 40 light-years away from Earth. That's exactly what researchers experienced when they unveiled TRAPPIST-1, sparking excitement and intrigue worldwide. In 1999, astronomer John Gizis and his team made a groundbreaking discovery: TRAPPIST-1, a tiny red dwarf star. The TRAPPIST-1 system was named after the Belgian-operated telescope in Chile after the 2 planets were found in 2016. By May 2016, the scientific world was buzzing with excitement. With the help of ground-based telescopes, NASA's Spitzer space telescope discovered 5 more orbiting TRAPPIST-1. Moreover, 3 of these planets were situated in the habitable zone, where conditions might support liquid water. The big announcement came on February 22, 2017, marking a significant milestone in space exploration. These TRAPPIST-1 planets are thought to be primarily rocky, and they're orbiting so closely together that
if you were standing on one of these planets, you'd actually see a lot of them sort of in the sky, whipping by on these very short orbital periods.
But there's more to the story. TRAPPIST-1 is estimated to be between 5.4 and 9.8 billion years old, making it older than our own solar system. Another intriguing aspect of TRAPPIST-1 is the potential for habitability on its exoplanets. With several of these planets located within the star's habitable zone, scientists are eager to investigate whether conditions conducive to life as we know it exist beyond our solar system. TRAPPIST-1 is currently among the most studied planetary systems beyond our own. It consists of 7 rocky worlds, similar in size and mass to our planet Earth, each with more water than all of Earth's oceans combined. Astronomers struggled to study these far-off worlds for ages, but everything changed with the launch of the James Webb Space Telescope. Astronomers have eagerly studied these planets' atmospheres to assess their potential to support life. Recent observations using the powerful James Webb Space Telescope, JWST, have provided some insights but posed challenges. Now, the most crucial question: how inviting is the TRAPPIST-1 system, and what's it like to live on these exoplanets? TRAPPIST-1 is among the smallest red dwarfs known, with a diameter of 52,300 miles or 84,169 kilometers, just 12% of the Sun's diameter and 8.9% of its mass. It radiates at 4,060 degrees Fahrenheit, which is less than half the temperature of the Sun's surface. With a radius of just 12% of the Sun's, TRAPPIST-1 is slightly larger than Jupiter, but significantly more massive. What sets the TRAPPIST-1 system apart is the unique resonance condition of its planets. They orbit in sync, forming a resonance chain connecting them together. This suggests a slow, peaceful evolution. Having a slow, peaceful evolution in the context of the TRAPPIST-1 system refers to the planet's unique resonance condition, which suggests a stable and harmonious arrangement of their orbits. This resonance chain, where the planets orbit in sync, indicates that they have not experienced major collisions with rogue asteroids or other disruptive events that could have significantly altered their trajectories. The planet's orbits are not chaotic over long timescales, which is typical for many planetary systems, and this stability suggests a slower and more peaceful evolution compared to other systems where major collisions and chaotic orbits are common. Astronomers can use transit timing variations, TTVs, to measure the masses and densities of the planets with high precision. The James Webb Space Telescope is an amazing telescope built to uncover the mysteries of the universe back when galaxies and stars first formed. What makes it special is its ability to study the atmospheres around distant planets outside our solar system. With its special tools like the mid-infrared instrument and the near-infrared spectrograph, it can analyze the unique light given off by these faraway objects. This helps scientists figure out what these planets are made of, how hot they are, and what their atmospheres are like. TRAPPIST-1, a red dwarf star, produces powerful flares multiple times daily. This frequent flaring activity poses challenges for astronomers studying the star's exoplanets, as the flares can complicate detecting atmospheric phenomena and identifying signs of habitability. The data also revealed significant interference from the host star itself. Unlike our Sun, the star has patchy hot and cool zones. These variations have affected the measurements, making it challenging to determine the precise atmospheres of the TRAPPIST-1 planets definitively. So, despite the challenges, what new insights into the TRAPPIST-1 system has this powerful telescope uncovered? The James Webb Space Telescope's exceptional precision enables scientists to detect brightness variations equivalent to examining 10,000 light bulbs and determining when 4 of them flicker out. This capability is crucial for studying exoplanets like those in the TRAPPIST-1 system. It allows scientists to analyze atmospheric phenomena and potential signs of habitability with rich detail and accuracy. Some good news with JWST observations confirms that none of these planets have thick, hydrogen-rich atmospheres like Jupiter. This discovery marks a significant step forward in our understanding. Recent observations with the James Webb Space Telescope also shed light on TRAPPIST-1b, the planet closest to its star. This rocky world is scorching, with temperatures soaring to 450 degrees Fahrenheit. Like Mercury in our solar system, it orbits very near its parent star, placing it far from the habitable zone. Any water on TRAPPIST-1b would have evaporated long ago despite the harsh environment. However, a recent study suggests that the other planets in this system might still maintain conditions suitable for water, whether in liquid or frozen form.
What the observers saw was that the day side of the planet is incredibly hot, indicating that there's no atmosphere that could possibly circulate heat around to the night side of the planet. And so our conclusion is that TRAPPIST-1b is most likely a bare, rocky surface with no atmosphere to speak of.
The article titled Atmospheric Reconnaissance of TRAPPIST-1b with JWST or NIRISS, Evidence for Strong Stellar Contamination in the Transmission Spectra is published by the monthly notices of the Royal Astronomical Society or MNRAS. This study focuses on the atmospheric composition of TRAPPIST-1b, one of the 7 terrestrial planets in the TRAPPIST-1 system, using data from the James Webb Space Telescope's Near-Infrared Imager and Slitless Spectrograph, or NIRISS. It is published by the Institute of Physics, a professional organization for physicists, and publishes several scientific journals. The authors present evidence for strong stellar contamination in the transmission spectra of TRAPPIST-1b, which has implications for the planet's atmospheric properties and habitability. In their study of TRAPPIST-1b using the James Webb Space Telescope, scientists couldn't confirm the presence of a secondary atmosphere consistent with previous observations of the system lacking thick, hydrogen-rich atmospheres. While JWST data indicated little heat redistribution on TRAPPIST-1b, challenges arose when using NIRISS to detect thinner atmospheres, with signals potentially contaminated by variations in the host star's light. Distinguishing between stellar noise and planetary signals remains difficult due to uncertainties in current stellar models for cool stars like TRAPPIST-1.
TRAPPIST-1c is really exciting because it's very similar to Venus in our own solar system. It's almost exactly the same size and the same temperature as Venus. And so we observed the planet searching for a Venus-like atmosphere. And in this case, we do not detect a very thick carbon dioxide atmosphere like Venus has. But it's possible that the planet has a small hint of an atmosphere, so it can't have very high surface pressure, can't have very much carbon dioxide, but it's possible that a little bit of atmosphere has remained.
However, the James Webb Telescope data debunked this notion, revealing that it lacks Venus's thick atmosphere. Based on the James Webb Space Telescope observations of TRAPPIST-1c, it has debunked this notion that it is a Venus twin in terms of its atmospheric properties. Although TRAPPIST-1c has a similar size and temperature to Venus, the JWST data suggests that it lacks the thick carbon dioxide atmosphere that Venus has. Instead, the atmospheric model for TRAPPIST-1c is consistent with a wide range of oxygen-carbon dioxide mixtures and surface pressures, indicating that it may have a thin atmosphere, if any. While it's hot on its day side, reaching around 225 degrees Fahrenheit or 107 degrees Celsius, the JWST observations have revealed that TRAPPIST-1c is now recognized as the coldest rocky planet ever studied. Temperatures reach as high as 230 degrees Fahrenheit or 110 degrees Celsius, which is significantly lower than the surface temperature of Venus. The infrared light emitted by TRAPPIST-1c does not match a Venusian atmosphere. TRAPPIST-1d, the lightweight among the planets in this system, weighs in at around 30% the mass of Earth, with a radius about 80% that of our home planet. Its relatively low mass suggests a probable absence of a dense atmosphere or an abundance of heavy elements. However, despite these characteristics, it shares some intriguing similarities with Earth, particularly in the amount of solar radiation it receives from its star. Situated right on the inner edge of the habitable zone, this planet's temperature, without an atmosphere, would hover around 48 degrees Fahrenheit or 9 degrees Celsius. What's really fascinating about this planet is its potential to hold a massive amount of water, around 250 times more than Earth. Whether it could support life depends on one key factor: albedo. Albedo measures how much light a surface reflects, with values ranging from 0 to 1. 0 indicating all radiation is absorbed by a perfectly black surface, and 1 indicating a perfectly white surface that reflects all incoming radiation. To compare with Earth, Earth's albedo is 0.3, and if TRAPPIST-1d's albedo is similar to Earth's, it might avoid becoming a runaway greenhouse state, even though water vapor acts as a greenhouse gas. Scientists propose that this distant exoplanet might be submerged beneath a vast global ocean. To sustain life in such an environment, a tidal heat flux 20 times more potent than what Earth experiences would be required. This is based on the assumption that life on this distant exoplanet would be similar to life on Earth, which is adapted to the conditions of our planet's climate. However, it is possible that life could exist in environments with different conditions, such as extreme temperatures or pressures, which would require different energy sources and heat fluxes. Like geothermal heat, this distinctive energy could foster chemical reactions within its immense aquatic expanse. Some organisms thrive through chemosynthesis, a process by which certain organisms can produce energy by converting inorganic compounds into organic molecules without the need for sunlight. This process differs from photosynthesis, which relies on sunlight to convert carbon dioxide and water into glucose and oxygen. The possibility of alternative forms of life on TRAPPIST-1d, not reliant on sunlight, suggests organisms thriving through this concept hints at the adaptability of life in extreme conditions, potentially utilizing sources like hydrogen sulfide or methane for energy. Chemosynthetic organisms could play a vital role in ecosystems, serving as a foundation for life in environments with limited sunlight. This idea expands our understanding of potential life diversity beyond traditional habitable conditions and underscores the resilience of life forms in challenging environments. Additionally, if this planet has a thin atmosphere, its twilight zone, where day and night blend, might also support habitability. Among the planets orbiting TRAPPIST-1, TRAPPIST-1e stands out. With its dense, potentially rocky composition, it closely resembles Earth. Positioned within the habitable zone of its host star, this intriguing world holds the promise of harboring life. Scientists speculate that TRAPPIST-1e may harbor greenhouse gases and boasts a thick, oxygen-rich atmosphere free from hydrogen. Here is the simulation from a scientific article titled High-Resolution Simulations of Future Climates on Earth-like Exoplanets by Fauches. The article was published in Geoscientific Model Development, and the authors are affiliated with the University of California, Berkeley. The simulation depicts a future climate scenario for an exoplanet named TRAPPIST-1e. TRAPPIST-1e is an exoplanet located within the TRAPPIST-1 system, and it is believed to be an aquaplanet, meaning a planet with a large ocean surface. The simulation assumes a nitrogen atmosphere with a trace amount of carbon dioxide, similar to Earth's atmosphere, for the exoplanet. The colors in the circles represent different surface temperatures, thermal radiation emitted, and reflected stellar radiation. The study simulates the future climate of an Earth-like exoplanet with a global ocean and an Earth-like atmosphere. Scientists use several climate models, including LMDG, ROCKE3D, and ExoChem, to analyze the amount of radiation emitted by the atmosphere at different wavelengths: red, green, and blue. This radiation data, along with reflected stellar radiation, helps determine the planet's surface temperature. The results show that different climate models produce slightly varying predictions for the exoplanet's future climate. The simulation is crucial for understanding exoplanet habitability, validating model accuracy, studying planetary evolution, advancing observational techniques, and assessing potential habitability factors beyond Earth. If TRAPPIST-1e held onto more water than Earth and Mars, maintaining it on its surface over time, its climate could closely resemble ours. This would almost make TRAPPIST-1e one of the most Earth-like planets ever discovered. In the simulation, synthetic transmission spectra were created for TRAPPIST-1e, a planet at the spectral coverage and resolution capabilities of the JWST NIRSpec and MIRI instruments. NIRSpec and MIRI are essential instruments on the James Webb Space Telescope designed for observing exoplanetary atmospheres like TRAPPIST-1e. These instruments play a crucial role in analyzing the transmission spectra of exoplanets, providing valuable data on their composition and properties. By simulating these spectra for TRAPPIST-1e, researchers can gain insights into the atmospheric characteristics of this exoplanet, helping to advance our understanding of distant worlds and their potential habitability. The different panels of the figure show the simulated atmospheric transmission spectra for various atmospheres at different wavelengths. Wavelength is measured in micrometers. Transmission spectra show how much light is transmitted through an atmosphere at different wavelengths. Here, the black lines show clear skies, and the colored lines account for the effect of clouds, hazes, or both. The text labels on the x-axis indicate the wavelength range for each panel. The y-axis shows the relative transit depth, which measures how much light the planet blocks as it passes in front of its star. This graph shows the brightness of a star system as a planet orbits around it. The dips and rises in the curve represent how much light the telescope is picking up at different points in the planet's journey. That's the total amount of energy blasting over from the star. Now, as the planet moves behind the star, that flux dips. That is because the telescope is not getting direct light from the star anymore. The planet is blocking it. We call that period an eclipse. Then, once the planet moves further, the telescope can see both the star and the bright side of the planet, the part labeled star plus planet day side. Over on the right side of the graph, things are similar. There's a section where the telescope only sees the star by itself, star alone, and another where it's catching the star along with the planet's night side, star plus planet night side. The really interesting part is this little dip here, marked transit. From our perspective, that's the moment when the planet actually crosses right in front of the star. The dip in brightness shows us the difference when some of the star's light is blocked by the planet. By measuring this dip, we can potentially learn more about the planet's atmosphere. Imagine a world where a mere 7 Earth days are already equivalent to a year, and the concept of day and night has a whole new meaning. All 7 planets in this system are tidally locked because of their proximity to the star. This means each planet is in a state of perpetual sunset or sunrise. Imagine being in TRAPPIST-1e and watching the reddish-yellow sky with the other 6 planets appearing like moons, some even larger than Earth's moon. On TRAPPIST-1e's sunny side, there could be livable areas with big storm clouds and strong weather, which are important for diverse ecosystems. But on the dark side, it's freezing cold with huge glaciers, making it tough for explorers. In our galaxy, there are 10 times more M-type red dwarf stars like this than stars like our Sun. They could be potential homes for life, offering billions of years for life to evolve and flourish in their vast realms. Red dwarfs, despite being typically dim, can occasionally experience sudden increases in brightness as it's going through solar flares. These flares, or outbursts of energy, can significantly enhance the luminosity of red dwarfs, making them temporarily much brighter than their usual faint appearance. This phenomenon adds a dynamic and unpredictable element to the behavior of red dwarfs, impacting their overall brightness and activity levels intermittently. TRAPPIST-1's star gives off smaller bursts than other red dwarfs, but its planets are so close together that these little flares still have a big impact. This means their auroras would be super strong and act as constant warnings for even smaller, more frequent flare-ups. Surprisingly, scientists think that these flares from TRAPPIST-1 might have helped life on its nearby planets. These bursts of energy could have kick-started the creation of important molecules, like amino acids, which are crucial for life. Surviving on TRAPPIST-1e, despite its potential for life, would require significant adjustments due to its frequent solar flares. We might need thicker ozone layers or artificial shields. A thicker ozone layer, like Earth's, or advanced technology to create artificial shields would be crucial to filter out harmful radiation from frequent flares. Another 2 ways to protect against solar flares is a strong natural magnetosphere like Earth's, or a sophisticated flare prediction system to allow inhabitants to seek shelter before the most intense radiation hits. Fortified shelters, acting as bunkers, would provide essential refuge during solar flares, minimizing exposure to harmful radiation. While TRAPPIST-1e's gravity, 93% of Earth's, wouldn't be a major issue, failing to cover during flares could lead to serious health problems. The constant threat of radiation exposure would be a defining characteristic of life on this intriguing exoplanet. TRAPPIST-1e's perpetual twilight also presents a unique challenge for plant life. The slanting sunlight casts long shadows, limiting the amount of light available for growth in some areas. If we could imagine adjusting to this, we can draw inspiration from the hanging gardens of Babylon, and tiered planter systems could be used. These would maximize sunlight exposure by strategically filtering light through different levels, mimicking nature's vertical ecosystems. There is also the potential plant adaptations like increased light absorption and bioluminescence. Plants might evolve to absorb more sunlight from the low-angled rays, potentially developing larger or more specialized light-capturing structures. In the most extreme scenario, some plants could even evolve bioluminescence, the ability to emit their own light. This would allow them to extend their growing hours and compete more effectively in the dim environment. New research as of 2023 by Joshua Christensen-Totten suggests TRAPPIST-1e, a potentially habitable planet, might have a significant atmosphere, unlike the first two planets in the system. However, studying its atmosphere is challenging due to thermal emissions mean the planet has a cooler temperature than closer planets, which demands longer observation times. Transmission spectroscopy means this method analyzes light passing through a planet's atmosphere during a transit. While applicable to TRAPPIST-1e, its star spots present challenges. The dark areas on the host star can be mistaken for atmospheric dips. High-altitude aerosols or tiny particles can block light and affect measurements, though less likely for TRAPPIST-1e. These challenges make it difficult to confirm the exact composition, like methane, water vapor, or CO2, of TRAPPIST-1e's atmosphere, but scientists are hopeful for future observations with advanced telescopes. Forget sunbathing on TRAPPIST-1f. This distant planet gets way less starlight than Earth, making it super cold, around -74 degrees Fahrenheit or -59 degrees Celsius. Without an atmosphere acting like a blanket, any water there would freeze solid. The same goes for the even further out TRAPPIST-1g and h. They might have water, but they'd probably be icy worlds too, without atmospheres to trap some heat. TRAPPIST-1g might be an icy world, but there's a chance it has a thick atmosphere thanks to its bigger size, about 30% more massive than Earth. If the planet maintains this atmosphere, it will distribute heat and sustain greenhouse gases, trapping heat from volcanic activity and keeping the planet warm enough for liquid water. Scientists even think a giant ocean might be hidden beneath the ice, concealing exotic life forms. It is estimated to reach an astonishing depth of 415 miles, or about 669 kilometers, dwarfing Earth's average ocean depth of about 2.3 miles or 3.7 kilometers. TRAPPIST-1h is the seventh planet and is located in the far reaches of the TRAPPIST-1 system. If you could imagine it in our solar system, it would be somewhere between Mars and Jupiter. This will give you an idea of how little light and solar radiation it gets from TRAPPIST-1, with temperatures dropping to about -148 degrees Fahrenheit or -100 degrees Celsius. Kathleen Mant, an astrophysicist and researcher, has played a significant role in studying the TRAPPIST-1 system, with a focus on the atmospheres and potential habitability of its planets. Her work involves examining the temperatures of these planets, assessing the possibility of a Titan-like atmosphere on TRAPPIST-1h, and using atmospheric retrieval modeling for broader studies. She suggests that TRAPPIST-1h might experience considerable volcanic activity, but these volcanoes eject water instead of lava. This process helps replenish the planet's atmosphere by releasing gases. Despite its remote location, TRAPPIST-1h can maintain its atmosphere, which includes nitrogen and methane. Past its prime, TRAPPIST-1 is an aging star, cooling over 7.6 billion years. It is assumed that it might have once given off intense heat that likely evaporated water on its nearby planets, trapping it in their atmospheres. Then, strong, stellar winds blew through, causing the water to drift away into space. Scientists are working hard to build better models of alien atmospheres based on real observations. In the past, we thought heat just escaped planets like smoke rising, but it turns out these atmospheres are way more complicated. Different gases act differently depending on where they are in the atmosphere. New discoveries question the notion that TRAPPIST-1 planets didn't get hot enough to melt their outer layers into molten rock. As a result, a lot of water might have remained locked within their rocks even after the star cooled down. Despite the likely presence of a huge body of water, the question of its habitability requires new research. Currently, these planets probably face extreme conditions. Even though red dwarfs live a long time, the 7 planets around TRAPPIST-1 have many eons ahead of them, going through lots of changes. What's really hot or cold today might turn into a friendlier environment for life as we know it in the future. The James Webb Space Telescope, JWST, promises further revelations about these Earth-like planets in the near future. With its latest advancements and discoveries, we are just scratching the surface. We'd love your insights on this intriguing revelation in the comments below. Thank you for joining us on this cosmic journey through the captivating TRAPPIST-1 system. From scorching hot rocky worlds to chilly icy terrains, these planets provide a fascinating glimpse into the diverse possibilities of exoplanetary realms. As we explore and understand these distant worlds, stay tuned for more James Webb Space Telescope revelations. Together, we'll uncover the mysteries of these Earth-like planets, getting closer to unraveling the secrets of potential habitability beyond our solar system. Don't forget to subscribe and turn on notifications to stay updated on the latest discoveries in space science. Until next time, keep exploring the wonders of the universe.